the topic where we left yesterday. So we discussed the measurement of relative permittivity of insulating sample material um, using sharing bridge. And along with the sharing bridge, I discussed on the last run. Sharing bridge we discussed, and then one testing setup, you can say, insulation testing setup that we discussed. So this is a experimental arrangement to measure the relative permittivity of the insulation sample, and it's very convenient. The salient point of this thing is with this topic, this method, is that it is very convenient. Setup is like that. You have to slip the material and then adjust the distance between the electrodes, um, and that's all. And measurement, you have to measure the thickness of the sample and the um, adjustment in the movable electrode that you have to measure. And then formula, you can see that very simple formula. With the help of these two readings, you can calculate the um, relative permittivity of the sample. What is the origin of this expression that we had already discussed on the last turn? So if anybody is having any doubt and anything which you are not able to understand, you can ask today. Otherwise, we'll start new topic. Anyway, now we are going to discuss Wien bridge. Wien bridge is basically used for measurement of um, frequency. So as you know that we have discussed different bridges. First set of bridges we discussed that were used for measurement of, those were used for measurement of inductance. Then we discussed another set of bridges that those are used for measurement of capacitance. And then will discuss the bridge which is used for measurement of frequency. Means if you are having a supply or a signal or oscillator whose frequency is not known, then we connect it as a source here in this bridge. And this is again a 4-arm bridge, and mm, we balance the bridge, and once your bridge is balanced, then um, then obviously we'll see what can be, because here um, all 4 arms should be known. Value of the arm component should be known. Unknown is your frequency. So how can we get the formula that we'll see? So first of all, we have written all 4 impedances, and then balance equation, and then simplification of this expression, and then you see, now we are having left side we are having a real and imaginary part, and right side and left side is having only real part. So obviously we'll equate real and imaginary parts. When we equate the real part, then we'll get this equation, and your imaginary part will be equal to 0. So that will fetch us this equation. And finally you can see that this is the equation um, through which we'll get the frequency. So this is very simple derivation, you can see. And when it is unknown, then so with this formula we can find out the frequency of the supply. Now, a few more things we'll discuss. Obviously, this bridge, as far as this bridge is concerned, because the balance equation, because we want to know the frequency, obviously your frequency term will be present in balance equation. It is must. So if your means if your supply or unknown frequency signal source is monotone, means it is having only one frequency, only then this bridge will be balanced. And this is true for this bridge only, not for this bridge only, but it is true for any bridge where the balance equation is frequency dependent. So if you are having more than one frequency, harmonics are present in the excitation, then obviously at a time you can balance the bridge for one frequency only. So if you are having more than one frequency in your supply, then you won't be able to balance the bridge. This is true for all the bridges which are having whose balance equation are frequency dependent. So obviously in this case, as far as Wien bridge case is concerned, here we want to determine the frequency only. Then obviously this is obvious that this balance equation should have frequency term. But as far as the other cases where we are measuring the inductance and capacitance over there, the phone. So in that case, you can means we will prefer those bridges whose balance equations are independent of frequency. So this is in this case we'll discuss certain issues. Now suppose in this case, if we are making R1 is equal to R2, this is possible. We can have two resistances R1 and R2 of same value, and similarly C1 is equal to C2. So here this is also possible. So the balance equation will result mm, uh, into this frequency formula will be reduced to this, and your this equation which we got after after equating real parts. So this will become equal to this. R4 by R3 will be equal to 2 if we are making. Now I want that you should interpret what exactly we are gaining out of it, and what. So all these things, if we are doing, so this is the outcome. Then what exactly we are gaining? Yes, please. I want that you should means, as far as expressions are concerned, that is okay. That is in front of you. That expressions are getting simplified. But what else, as far as the bridge circuit is concerned, bridge balancing is concerned, bridge balance equations are concerned, what we are gaining in those terms? जी बताइए.
So frequency,
Eh?
you're
नहीं,
gaining
frequency is fine. What I'm saying, when we are making R1 and R2 equal and C1 and C2 equal, then your equations, your balance equations, that whatever balance equation you got, one balance equation is this and another balance equation is this. So it is reduced to this simple form. That is the thing, that straightforward it is visible here. What else we are gaining because of this particular modifications, you can say? हमें कोई भी. You see, your what is the meaning of this? How will you how will you interpret this expression or decipher this expression? Now listen carefully. If you are not able to because you people are not applying yourself, so you are not able to. It's very simple thing. Now with this set of values of Wien's bridge components, means Wien's bridge arms, with these sets of values, means we are taking R1 and R2 equal and C1 and C2 equal. Then for bridge to be balanced, these two equations should be satisfied. Then you see that it is giving one more condition, that R4 should be equal to R4 should be equal to twice of R3. R4 should be equal to twice of R3. Twice of R3, sorry. Is it fine? Now, if in this bridge, whatever bridge we have designed, we are making R1, R2 equal, C1, C2 equal, then another condition for bridge balance is your R4 should be twice of R3. If these things are true, then only one balance equation we are supposed to satisfy, because this is already satisfied. We have chosen the components R4 and R3 such way that which is satisfied. It is possible that whatever value of R3 you are taking, twice of this value it will take R4. Now you are balancing the bridge, means satisfying this equation only. So we do not require. So this equation can be satisfied either by varying R or by varying C. Obviously, we don't prefer to vary C to have a variable capacitance. So obviously we'll have a variable resistance. So variable resistance, meaning of varying the resistance here, means if we vary R1 and R2 simultaneously, so this bridge will behave like a single control bridge. We don't require two components to be means variable. Only one. Although here we are varying R1 and R2, but we are considering it as a one control, because same amount of change you require in R1 as well as in R2, and that's why it is shown here that R1 and R2 both are connected with the mechanical link. So whatever changes we are making in R1, simultaneously it will. So by moving this, we can balance the bridge. No other variable term is required. So this is how, by having these values, this kind of values of the by choosing R1 is equal to R2 and C1 C2, your bridge is becoming single control bridge, and there will not be any sliding balance problem in this bridge, because it is a single control bridge. With the help of single component, you are balancing the bridge, and only one balance equation you are supposed to balance. So there will never be any sliding balance problem, and it will be very easy to um, balance the bridge. So this is what we achieve with these set of values of the components. Otherwise, if you are not doing this, then it is as good as any other four-arm bridge, and accordingly it will have, because these two equations you have to satisfy simultaneously. If you are not taking R1 is equal to R2 and C1 is equal to C2 in this bridge. In any case, whatever is the arrangement, accordingly you choose your formula and you balance the bridge. Only then this formula will be valid, and note down the values, and then you can find out the frequency value. This is how Wien's bridge is used for measuring the frequency. So if anybody is having any question regarding Wien's bridge, you can ask, please. Am I audible to all of you?
Yes, sir.
Okay. You don't have any question. Now, This bridge is suitable for measurement of frequency from 100 hertz to 100 kilohertz, and accuracy between, it's very good accuracy, zero point 0.1 plus minus 0.1% to point plus minus 0.5%. That's what I had told you, that your applied voltage should be purely sinusoidal, because if your signal is not sinusoidal distorted, this means it is having other frequency components also. So when it is, if your supply is having harmonics, then it is not possible to balance the bridge, Wien's bridge, or any other bridge whose balance equations are frequency dependent. Now I want that you solve this problem. This is based upon the Wien's bridge. You solve this problem, please, all of you. You apply yourself, and you will be able to solve it, please. And respond your roll call also. Roll number 1,
Present, sir.
2,
Present, sir.
3, 4, 5, 6,
Present, sir.
7, 8, 9, 10. Aman Malik's problem.
Sir, R2 400 ohm.
R2 is 400 ohm. And frequency?
Calculate.
So in this case, you can see that your C1 is not equal to C2, and R1 is not equal to R2. So obviously expanded formula you will use.
Approx 4 kilohertz.
4 kilohertz.
Sorry.
So 398 hertz and 400 ohm. Anyway, main thing is that you
Yes,
should
sir.
be able to balance the
397.8.
bridge, derive the balance equation, and then you put the values. Okay. If anybody is having any difficulty, you can ask, please. Anyway, now we'll discuss how can we measure mutual inductance. If two coils are in vicinity, means near each other and having a coupling, then I'm not able to rotate this. So it's very simple. Suppose how can we measure the mutual inductance? Suppose we are having two coils, and they are, means two coils, obviously if they are kept near each other, so their flux will, one coil's flux will link another coil flux will link the first one, and this is called, means self inductance is basically flux of that coil links itself per unit current is called self inductance. But mutual inductance is basically the flux of one linking another, and flux of first one linking another one is linking to the first one per unit current. That is called mutual inductance. So whenever there are two fluxes, they are two coils, they are kept near each other, then because of the flux linkage, there will be the mutual inductance also. So when mutual inductance means when the flux is in same direction, you can see that we put dot here and we put dot here. So this means the polarity, kind of polarity of the electromagnet that will be formed by these two coils. Their poles are in the same direction, so fluxes will be in the, means like fluxes are aiding each other, so they are in same direction. So the equivalent inductance of this series connected coils, which is having mutual, whose flux is also linking with each other, will be L1 plus L2 plus twice of the mutual inductance. Now when the connection means, now we can connect this terminal here, so it will be like this. So here you can see that fluxes are, as per the polarity, fluxes are basically opposing each other. So in this case, equivalent inductance, our objective is to measure the mutual inductance that exists between these two coils. So this is the experiment that we are doing. So in this case, the equivalent inductance will be L1 plus L2 minus 2M. Now what will we do? We will take the difference of these two, then difference of these two will be equal to your mutual in 4 times the mutual inductance. So mutual inductance will be 1/4 upon difference of these two equivalent. So this method seems very simple, but this method works only when the two coils are having good coupling, means most of the flux are basically linking with each other in the given direction. So this method, otherwise you will find that LE1 is equal to LE2, and you will take the difference, it will be 0 if coupling is not good. So this method is, although very simple, but it is not it is having sensitivity issue. Means you find that LE1 and LE2 are equal if coupling is obviously very good, means most of the flux produced, these two, they are linking each other, these two coils, then you will have obviously difference between equivalent inductances. So bridge method is used, which is very sensitive. And so one of the bridge which is used for measurement of mutual inductance is called Heaviside mutual inductance bridge. So in this case, you see this is the bridge, and this is the mutual inductance coil. These two coils, which are means they are coupled, you can say, and we are interested in finding out the mutual inductance of this. So this Heaviside bridge is used to measure the mutual inductance, and this again it seems a bit different because of the mutual inductance arrangement here, but that is the requirement. And although it is a 4-arm bridge, but the easiest way of finding the balance equation is a bit different, although concept remains same. So in any case, bridge will be balanced as usual, as means process of bridge balancing remains same. As we balance the other bridges, same way this bridge will also be balanced by basically varying the variable components. Once your bridge is balanced, so obviously this branch will have same voltage as this branch, means this branch will have same voltage this, and this branch will have same, only then your B and D will sit at the same potential. So when this is true, when bridge is balanced, then this will be true, that voltage drop across this will be same as voltage drop across this that I had written here, and voltage drop across this will be equal to voltage drop across this branch that I had written here. So here is this term, you can see I1 plus I2 j omega m, because this current will basically producing the flux, and that is linking this coil, plus I1, and other thing means it's very simple, I1 R1 plus R3, you see, um, I1, this whole is equal to this whole. So I1 R1 plus I1 R1 plus I1 R3 plus I1 J omega L1. That's what it is written here. So this is done, and then this will be equal to this. So I2 is equal to R2 plus. So this is the condition when the bridge will be balanced. Now we'll simplify this. This one is very simple. Here there is no mutual inductance term. And now our unknown parameter is M. All other parameters are known. So what we do, just to simplify it, we are writing I1 in terms of I2. So from this equation, I1 will be equal to I2 into R4 upon R3. So that's what we have written here. So this equation is in terms of I2 only. So all I2 will from left side and right side get cancelled. Now we are having equation in terms of the impedance only. Now we are required to simplify it, and once it is simplified, then left and right real and imaginary parts will be equated. So now you can see that when we equated real parts, we get this, and when we equated imaginary parts, we got this equation. So from this equation we can find out the R1, and this equation is we can find out the mutual inductance, and that is what is the objective of our. So in this case, obviously L1 is the self-inductance of secondary of the mutual inductor. Mutual inductance means it can be a transformer coil also, which is having primary and secondary winding. So suppose we are making R3 is equal to R4, that we can do very easily. R3, we can have same value of these two. So this will simplify your expressions to. So now once you will make R3 is equal to R4, then these equations will be simplified like this. M is equal to L2 minus L1 upon 2, and R1 is equal to R2. So this is how Heaviside bridge is used for measurement of mutual inductance. Here it is shown that it can also be used for measurement of self-inductance of a coil L2, suppose. So we can, but in that case you should the mutual inductance should be correctly known, and that is generally not preferred. But in any case, this is one of the now this bridge is modified for measurement of self-inductance in terms of the mutual inductance. That is called the modified version application I told you, and it is called Campbell's modification of Heaviside bridge. So in this case, another means here it is written the Campbell's this is used, means modified bridge is used to measure self-inductance in terms of a mutual inductance. So in this case, another coil has been added here, you can see, and this is your balancing coil, and this is your test coil, whose inductance we are interested in finding out in terms of the mutual inductance. Obviously, whatever mutual inductance you are taking, it is basically it should be correctly known. So otherwise this bridge is same as the Heaviside bridge. So now in this case, procedure is a bit different. Here in this case, what we do, it is written, we short the switch places in place across the R2 end. First of all, we short the switch. Two set means once first of all we balance the bridge with only balancing coil in the circuit, and then we open it. So when you open the switch, obviously both the coils will be here, so that this equation, because bridge remains same, so this equation L2 is equal to, it will be L2 plus L2 plus L. This will be your equation. L2 plus L. And when switch is closed, means your testing coil is basically shorted. Only this coil, balancing coil, is in the circuit. And then again bridge is balanced, and this will give you whatever value you will get. It will be only L. Then we'll subtract this equation by this, then we'll get only L2, and this is the resultant. So in this case, you see your M means your mutual inductance is basically variable here, M1 and M2. And the values whatever way. So obviously this mutual inductance should be standard and it should be known. So in terms of mutual inductance, we are measuring the self inductance, and it is done with the help of Heaviside Campbell's modification of Heaviside bridge. Similarly, R2, when it is open, then we'll have R2 plus R, and when it is closed, then we are having R only, and by subtracting these two, we'll get R2, means your coil inductance, and this is coil inductance, this is coil resistance. And when we'll make it R3 is equal to R4, then these two expression will get simplified to this extent. Now, you see, in this case, whatever we have done by subtracting is we are performing two-step experiment, and then we are subtracting these two. So you can see that this method is very good, and it is sometimes it is preferred, because whatever lead resistance and common type of error these equations will be having, they will be taken care of, because we are subtracting, then all those common error will get cancelled. And generally lead resistance and lead impedance is an issue, and if we are subtracting two readings, so obviously that those common kind of error will be taken care of. And this is not confined, this particular method or way of measurement is not only confined to the bridges, it will confine to any measurement system. Means it is extended to any measurement system where it is done, then common type of error will be taken care of. So this is how mutual inductance can be measured in terms of the self-inductance. And in this Campbell's modification of Heaviside bridge, the self-inductance of a coil can be measured in terms of mutual inductance. So this is how these two bridges are used. If anybody is having any question regarding these two bridges, you can ask, please. Anyway, I'm summarizing this unit. This was the last topic in this unit. Now I'm summarizing that in this unit we discussed mini bridges. Obviously, all kind of bridges we didn't discuss here. There are many more bridges which are also used for measurement of whatever parameter we discussed here, measurement of whatever parameter. But whatever in your course, all bridges we have discussed. So we discussed a set of bridges which are used for measurement of inductance. Then another set of bridges, AC bridges, we discussed to measure the capacitance. Then Wien's bridge we have used for measurement of frequency. Then we use Heaviside mutual inductance bridge to measure the mutual inductance in terms of this self-inductance. And finally, we discuss the Campbell's modification of Heaviside bridge for measurement of self-inductance in terms of the mutual inductance. So all these things we have discussed in second unit, and I'm closing second unit here. Now I'll start the third unit today. Sensors. Now I'll discuss what is sensor. I want the answer from you. You people are, means in daily life we are using sensor, many sensors we use. Now I want, what do you mean by, what do you understand by sensor? हाँ भाई बताएं आप.
The sensor is a device which detects signals.
Which detects signals. Okay.
So
Really?
like circuit breaker is a sensor.
Circuit breaker is a sensor. किस ईयर में आ गए हो तुम? थर्ड ईयर में? यार रिले को कहा होता सेंसर तो कुछ समझ में आ रहा था, तुमने सर्किट ब्रेकर को ही सेंसर बना दिया. और बताइए. ठीक है, ओके, एंड थैंक यू दैट यू आर रिस्पॉन्डिंग.
Sir, a sensor is a device that detect and respond to some type of input from the physical environment.
Okay, better, much better, much better. What is the purpose of sensing?
Uh, Sir, especially it is used to measure the physical quantities such as light, pressure, temperature, humidity.
Good,
Uh,
very good,
So, sir,
very good.
in three-phase transmission line, it is used to detect fault.
That is relay. That is protection system. That is not sensor.
Sir, but it gives signal to the
What gives
circuit
signal?
breaker.
What gives signal?
The relay.
Relay is not sensor. Relay is relay. Relay senses fault. It senses fault current or for fault voltage or whatever parameter. If there is any abnormality, then it accordingly it send the signal to the circuit breaker. But it is not sensor. Any other person want to speak about the sensor? Yes, please.
Sensor is a device which sends the data and send it to the microcontroller to perform several actions.
Several actions. It's better. Whatever earlier person told, that was better. Anyway, just a minute. Let me find out if there is any. Okay.
Sir, actually, sensors are widely used in the IoT devices.
IoT devices. That is the application. That is the application. Sensor is basically a device which converts one type of parameter into another suitable parameter which facilitates the measurement of that parameter. Like this is your sensor. Like we want to measure this parameter x, then we convert it into another suitable parameter, and this conversion is done with the sole objective of measurement of parameter x. And this is done because it is easy and economical to measure parameter y. That's why it is converted into parameter y. Although our sole objective is to measure this parameter. So this conversion is to facilitate the measurement of this parameter. And the device which performs this conversion is called sensor. So you're understanding what is sensor? Sensor basically converts one type of parameter into another type of parameter solely to facilitate the measurement of the first parameter. This is the device which is used to perform this kind of conversion to achieve this measurement facilitation in measurement is called sensor. And the system is called instrumentation system. If somebody asks you what is instrumentation system, then it is sensor based measurement system. Instrumentation system is nothing but the sensor based measurement system. Is it clear to all of you?
Yes, sir.
Now
Yes, sir.
there is a class of sensor. There is a class of sensor which basically converts non-electrical parameter into the electrical parameter. Obviously, the objective remains same, that this conversion of a non-electrical parameter into electrical parameter we are doing to facilitate the measurement, accurate measurement, obviously, accurate and economical measurement. I told you the reason also. So this class of sensor, sometime it is called transistor, but nowadays the transducer and sensors are used interchangeably. Now I'm giving you the example, like RTD, resistance temperature detector. This is an electrical sensor which converts the temperature into the resistance, whereas the resistance is the electrical parameter and temperature is a non-electrical parameter. So non-electrical parameter is converted into the electrical parameter, and this electrical parameter is measured. You had already studied many methods by which you can. So now question arises. Now there are numerous sensors which converts different kind of non-electrical parameter, or rather you can say industrial parameters. To convert, it converts non-electrical parameters into the electrical parameter. Why do we require this conversion at all? Obviously, okay, sensor is done. What is sensor? We have discussed. Now why do we require to convert the temperature into resistance, the pressure into resistance or capacitance, or and so on? Why do we require that?
So because the manipulation of the electrical signal is rather simple as compared to the other physical quantities.
But that is a secondary requirement. First of all, if we are measuring anything, our main objective is to measure it accurately.
Yes.
Afterward, our main object, actually reason is that it is possible to measure the electrical parameter very accurately at low cost. Means you want to measure the voltage, then 100 rupees voltmeter will work for that. If your temperature, you want to measure the temperature in the room, is converted into the resistance, and that resistance is converted into the voltage, now you require a very simple voltmeter to measure the temperature, and this voltmeter is very accurate. So accuracy with economy. Whenever we are measuring anything, our main objective is the accurate measurement. Nobody measures anything inaccurately. Nobody want to measure anything inaccurately. Means if you purchase a watch, and watch measures the time, and if it is not measuring the time accurately, you will abandon it if somehow you are able to purchase it. नहीं भाई सही टाइम नहीं देती, I won't require it. आप उसको रख दोगे चाहे जितनी अच्छी घड़ी हो, है ना? और अगर दुकानदार बताए कि this watch gives an error of 1 hour or 2 hour or 50 minute or 30 minute or 20 minute or 10 minute or even 5 minute, you'll say नहीं भैया ऐसी घड़ी नहीं चाहिए, जो सही टाइम दे वही दो, है ना? So our main objective is to measure the accuracy is in any kind of measurement. Accuracy is the main objective. Now, if this accuracy, we are getting the accuracy with a lot of, means it is costly, then we'll think twice. We'll think twice. You know? If you are going to purchase a scale, and although scale is very accurate, but they are saying it is 50,000 weighing scale I am talking about, it is of 50,000 rupees, तुम कहोगे यार फिर क्या जरूरत है. और अगर कोई कहे कि भाई ठीक है, अच्छा है, it is not as accurate as that one, but it is good, it is having good accuracy, but I am giving it in 500 rupees or 1,000 rupees or 2,000 rupees, you'll say हाँ ये चलेगा. So obviously, economy, accuracy with economy. So this sensors, especially electrical sensors, they offer this particular feature, that once you are able to convert the non-electrical parameter or any industrial parameter into the electrical parameter, then with the electrical way, because the electrical measurement methods are very accurate. You have studied also, like if we are having any sensor which converts the non-electrical parameter into resistance, then you are having a numerous method, and you know their pros and cons, and you will use suitable method to measure it accurately. So and if you are using a VT stone bridge, you know VT stone bridge is also not very costly, and even voltmeter meter method will work. It also gives you the decent accuracy. So this is why we want. And then in addition, once whatever somebody told, some of your friend, that apart from this, once you are able to convert your signal measurement parameter into electrical signal, now it will have all the advantages electrical signal has. Means you can process it, you can convert it into the numbers, and then you can play with the numbers, you can put it, you can interface into the computer, then you can transmit it also. So, and you can analyze, you can make a graph, anything in it, many things is possible. So those all are the additional things, additional attractions. So that's why sensors are used widespreadly, even in our daily life also. You see your AC is having a sensor, your fridge is having a sensor, your mobile phone is having many sensors, and many things are there, and your satellite is having sensor, your aeroplane is having sensor. Everything is equipped with the sensor, and we are surrounded by the, wherever there is automation, sensor is required, because you have to monitor the parameter, and for monitoring and measuring the parameter we require sensor. So this is why, how this is so I'm able, I tried to explain you at the starting, that what is sensor and what is its utility, and another class, one class of very important sensor that converts the non-electrical parameter into electrical parameter is basically used because of the high, it provides high accuracy at the lower cost. And apart from this, once your signal is converted into the your parameter is converted to the electrical signal, many things are possible with that. So all these privileges we get with the help of sensor based measure and system. Sensor based measurement system is called instrumentation system. It is called instrumentation system. Now I'm closing today's discussion here. Now respond your roll call. Other students should respond your roll call.